All right, buckle up, everybody, because today we are diving headfirst into some seriously heavy stuff. Black holes. Those cosmic monsters that seem to defy the laws of physics.
Yeah, and we're going way beyond the typical black hole basics today. You guys send in a mountain of research. Some of these papers dense, let me tell you.
But that's why we're here, to break it all down, sift through the astrophysics jargon, all those equations, and pull out the most mind-blowing insights, of course. We'll make sure you come away with enough black hole knowledge to impress even, like, the biggest science buff you know.
Exactly. We're talking about the latest findings on how these things form, what happens at the edge of a black hole, the event horizon, the really bizarre physics happening there, all that good stuff.
So to understand all that, we got to start with the basics. I mean, we're dealing with objects so massive they literally warp the fabric of space-time itself.
Right, and for that, we have to talk about Einstein.
The OG space-time celebrity.
His theory of general relativity, it totally revolutionized our understanding of gravity. It wasn't just a step forward, it was like leaping from, I don't know, using an abacus to having a supercomputer. You know what I mean?
Totally.
Before Einstein, we thought gravity was the simple force between objects, bigger objects, stronger pull. But what he showed us is that gravity is all about the bending, the warping of space and time. It's wild.
Okay, so less like an invisible string pulling things together and more like,
What?
a bowling ball on a trampoline.
Yeah.
It creates a dip and other objects kind of roll towards it.
Yeah, you got it. The more massive an object, the deeper that dent it makes in space-time and the stronger its gravitational pull.
Okay, I'm following so far. So how do we go from a dented trampoline to the actual birth of a black hole? Where do stars come into the picture?
Well, it all begins with the life cycle of stars, these giant nuclear fusion reactors scattered throughout the universe.
Right, stars. I've heard of those.
They spend the majority of their lives fusing hydrogen into helium at their core. Massive energy creates outward pressure, and that's what counteracts the inward pull of gravity.
Ah, the classic cosmic tug-of-war, right?
Oh.
Gravity versus fusion, battling it out.
Exactly. But even the mightiest star, they eventually start to run out of fuel. And when that happens, well, gravity starts to win the tug-of-war. Now, what happens next really depends on the star's initial mass.
Okay, so size matters in the cosmic realm.
Oh, absolutely. A smaller star, like, say, our sun, it'll eventually become a white dwarf. That's a super dense object, but about the size of the Earth.
White dwarfs, those are like the laid over embers of a dead star, right?
Exactly. But when you've got those massive stars, that's when things get way more exciting.
Okay, I'm intrigued. Tell me more about what happens with these stellar heavyweights.
So picture a star significantly larger than our sun, reaching the end of its life. Fusion in the core, it starts to sputter. Gravity starts to take over, crushes the core inward.
Intense. So what happens? Is it just, I don't know, implode?
Well, something has to give, right? That's where electron degeneracy pressure comes in.
Electron degeneracy pressure. You're
Right.
going to have to elaborate on that one for me.
I know, it sounds complicated, but it's actually pretty simple. Imagine you're trying to cram like 100 people into a phone booth, right? What's going to happen?
Chaos. And probably a lot of pushing and shoving.
Exactly. They're going to push back, right? So that's kind of what's happening inside that collapsing stellar core. Electrons, they're these tiny particles, and they really hate being squeezed together. So they push back against the crushing force of gravity.
So it's like a last stand for the core, fueled by these rebellious electrons.
Pretty much. But even the bravest electrons, they have their limits. If the star's core is massive enough, we're talking about 1.4 times the mass of our sun, gravity is going to overpower even that electron degeneracy pressure.
And that's when things go supernova.
That's one possibility, yeah. We'll get to that in a bit. But here's where it gets really interesting. Even the death of a star, it actually depends on what it's made of.
Wait, you're telling me that stars have, like, different ingredients? I thought they were all just big balls of burning gas.
Well, they are, essentially. But one crucial factor is a star's metallicity.
Metallicity. Like, how much heavy metal a star listens to.
Not quite, though I kind of love that image. Metallicity in astronomy refers to the amount of elements heavier than hydrogen and helium that a star contains.
Okay, so how does a star's heavy metal playlist, so to speak, affect how it goes out?
Think of it this way. Stars with higher metallicity, they're like the cosmic rock stars.
Yeah.
You know, burning bright, living fast, but they also shed a lot more of their mass through these things called stellar winds.
Stellar winds. Is that like, I don't know, burping out particles or something?
Basically, it's these powerful streams of particles they eject throughout their life cycle.
Wow. Dramatic much.
Right. And all that mass they're shedding, that plays a huge role in whether a star can even become a black hole in the first place.
How so?
Because for a black hole to form, you need a core massive enough to collapse under its own gravity. But if a star has lost too much mass from those stellar winds, its core might not be heavy enough, to go all the way to a black hole.
So it's like a delicate balance. It needs enough mass to collapse, but not so much that it blows itself apart before it gets there.
Exactly. Delicate cosmic balancing act.
Okay, so let's say we've got our massive star, just the right amount of heavy metal. I like that.
Yeah.
And gravity's about to win that tug of war. What happens in those final moments?
Things get pretty intense. The core collapses in on itself super fast, and the outer layers of the star, they get blasted away in a supernova explosion.
Ah, supernovae. Those are some of the brightest events in the universe, right?
Oh yeah, for a little while, a single supernova can outshine an entire galaxy. It's amazing. But what we're really interested in, what's left behind, is that core.
Right, because if the core is massive enough, then it becomes
A singularity.
Right, a singularity. Which is, remind me again.
It's where all the matter in the core is crammed into a space with zero volume. Everything compressed into an infinitely small point.
Infinitely small. As in smaller than an atom, smaller than a proton.
Smaller than anything. It literally breaks down our current understanding of physics. It's that wild.
Okay, yeah, that's where my brain starts to melt a little bit.
Happens to the best of us, don't worry.
So we've got this singularity, this point of ultimate compression. But what about the black hole itself? Is that just the singularity, or is there more to it?
That's where the event horizon comes in. Imagine a sphere, invisible, surrounding the singularity. That sphere, that's the point of no return.
So once you cross the event
You're
horizon,
not coming back. The gravity inside is so strong that nothing, not even light, can escape.
hence the name black hole, I guess.
Yeah.
But if we can't actually see them, how do we even know they're out there? That seems tricky.
That's where things get really clever. Astrophysicists have figured out ways to detect these things indirectly.
Okay, I am all ears, because I have no idea how you'd even begin to look for something that doesn't emit light. It'd be like searching for a black cat in a coal cellar.
Well, one way is to look for their effects on other objects. Remember how we were talking about massive objects warping space-time?
Yeah, the bowling ball on the trampoline.
Exactly. Black holes, they take that warping to the extreme. So if there's a black hole nearby, we can observe its gravitational effects on the things around it, stars, gas, you name it.
So we'd see stars behaving strangely, like orbiting around an empty point in space.
Yeah, like a cosmic dance with an invisible partner. And by studying their movements, we can calculate the mass of that invisible object and figure out if it's likely a black hole.
That's some seriously impressive detective work. So we've got stars doing pirouettes around black holes. Are there any other telltale signs we can look for?
There's this cool thing called gravitational lensing.
Lensing, like a camera lens.
Yeah, kind of. Imagine some distant galaxy shining its light towards us, right? Now, if a black hole happens to be between us and that galaxy, its gravity can actually bend the light coming from that galaxy.
So the black hole acts like a giant magnifying glass in space.
Exactly. It distorts the image of the galaxy behind it. And by studying these distortions, we can infer the presence of a black hole.
Wow, it's like using the fabric of space-time as a telescope.
You got it. And there's one more clue. Gravitational redshift.
Hit me with it.
You know how light loses energy as it tries to escape a strong gravitational pull?
Yeah, like climbing out of a deep hole, right? Takes effort.
Right, so as light struggles to escape a black hole, its wavelength gets stretched out, which makes it shift towards the red end of the spectrum.
So by looking for that red shift, we can tell if a black hole is nearby.
Exactly. It's like a fingerprint, a signature of its powerful gravitational pull.
This is all so cool. It's like the universe is putting on a show just to help us find these hidden giants.
And we're just getting started. These research papers you sent, they dive into some really cutting-edge discoveries about how these black holes form.
Okay, you've definitely piqued my curiosity.
Yeah.
Let's get into it. What kind of groundbreaking stuff are we talking about here?
So these papers, they're looking at black hole formation in a whole new way, like incredibly detailed simulations, not just of a star collapsing, but of the movements of individual particles within that collapse.
Whoa, okay, so instead of the big picture, they're like zooming in on each little speck of dust in the cosmic windstorm. That seems ambitious, to say the least.
It's hardcore astrophysics, for sure. But what they're finding is that even tiny particles, electrons, protons, things like that, they can actually push back against the gravity of a collapsing star.
Wait, seriously? How can something so small even register when you're talking about forces that can warp space-time?
It's all about the charge, you see. These particles, they're not just mindlessly falling in, they're electrically charged, and those charges, they interact.
So it's like a cosmic game of bumper cars is happening inside this collapsing star.
Yeah, kind of. And depending on that balance of charge and mass, the core might not just go quietly. It might, like, sputter, bounce back, even maybe form something weirder than we can currently wrap our heads around.
Weirder than a black hole. Okay, now
Mhm.
that's saying something. But how do we go from these simulations, these models, to actually observing what's going on out there in the universe?
That's the exciting part. We're living in a time where we've got these incredible new telescopes coming online. The extremely large telescope, the ELT, being built in Chile. That's going to be a game changer.
ELT, huh?
Yeah.
Catchy? I'm guessing extremely large is not an understatement.
Not even a little bit. This thing's going to have a mirror bigger than a basketball court. The light gathering power is insane.
Mhm.
We'll be able to study the environments around black holes in more detail than ever before.
So we're talking like actually seeing the gas swirling around, maybe even glimpsing the event horizon itself?
Well, we can't see past the event horizon. That's the point of no return, remember? But the ELT, it's going to allow us to study the light coming from around a black hole with unbelievable precision. Might even reveal clues about the very fabric of space-time itself.
Okay, that alone is mind-blowing. But what about those telescopes that can see beyond the visible spectrum? What about cosmic radio waves, all that?
Don't worry, we've got that covered too. Gravity, that's another instrument. This one is being added to the Very Large Telescope Interferometer.
Gravity. Okay, you guys are not messing around with these names, huh?
Right. But gravity, it's going to be able to track the movements of stars and gas clouds around black holes with ridiculous accuracy.
So what you're saying is we'll be able to basically track like a grain of sand from thousands of miles away.
Pretty much. It's that precise. And even with all that, even with all the amazing technology and research, it feels like every answer we find just leads to more questions.
It's true. And that's what makes black holes so fascinating. They push the boundaries of what we know about the universe. They challenge our understanding of physics, gravity, reality itself.
Exactly. And that sense of wonder, that drive to keep exploring, that's what it's all about.
It really makes you realize just how much more is out there to discover, how much we don't know. It's humbling, in a way. But hey, on that note, I think it's time for us to maybe come back from the edge of the cosmic abyss for now. To everyone listening, keep looking up, keep asking those big questions, and we'll catch you in the next deep dive.